What if I told you the secret to how AI models actually get so incredibly smart isn't magic, but a simple, elegant mathematical dance? We see AI creating art, writing code, even diagnosing diseases, but have you ever stopped to wonder how they learn from their mistakes? At its core, an artificial neural network is inspired by the human brain. It's a system of interconnected neurons organized in layers. Data enters one end, passes through these layers, and a prediction comes out the other. This journey is called the forward pass. But here's the thing, when an AI first starts, its predictions are often wildly wrong. It's like a student taking a test for the very first time. They'll make mistakes. The crucial part isn't making the mistake, but learning from it. The process that allows neural networks to learn from their errors, to fine-tune themselves and get smarter, is called backpropagation. It's the mathematical backbone of almost every AI breakthrough you've seen. Imagine a complex factory assembly line. Raw materials go in, pass through many different workstations, and a finished product comes out. Each workstation adds something, changes something. This is our neural network. Now, let's say the final product has a defect. It's not quite right. This defect is our AI's error. How do you figure out which workstation, or which combination of workstations, contributed most to that defect? Backpropagation starts at the end. We calculate the error, the difference between what the AI predicted and what the correct answer actually was. This error is a numerical value, a signal. Instead of just stopping there, this error signal is then sent backwards through the network, from the output layer, through the hidden layers, all the way to the input. It's like the factory manager tracing the defect back through each workstation. In a neural network, each connection between neurons has a weight, and each neuron has a bias. Think of weights as the strength of a connection, and biases as an extra nudge. These are the knobs the AI can turn to change its output. As the error travels backward, backpropagation uses calculus to figure out how much each weight and bias contributed to the final error. It calculates something called a gradient. Imagine you're on a mountain, and you want to go downhill the fastest way possible. The gradient tells you the steepest path. The core mathematical tool here is the chain rule from calculus. It's like a series of dominoes. If pushing the first domino affects the second, and the second affects the third, then the first domino ultimately affects the third. Backpropagation uses this to link the error at the end to tiny adjustments needed at the beginning. So, for each weight and bias, backpropagation calculates a gradient, a number that tells us two things. First, which direction to adjust the weight, increase or decrease it, to reduce the error, and second, by how much to adjust it. Once we have these gradients for all weights and biases, the network updates them. It slightly adjusts each knob in the direction that reduces the error. This small adjustment is one step of learning. How big of a step does the AI take when adjusting these knobs? That's controlled by something called the learning rate. A high learning rate means big steps, risking overshooting the correct answer. A low learning rate means tiny steps, making learning very slow. This entire process, forward pass, calculate error, backpropagate, update weights, is repeated thousands, millions, even billions of times. Each cycle, the network gets a little bit better, a little bit more accurate, until its errors are minimal. This is how it learns. Backpropagation is incredibly powerful because it allows complex, multi-layered neural networks to learn efficiently, even with millions of parameters. It's the reason deep learning works and why AI has made such monumental strides in recent years. So, the next time you see an AI do something amazing, Remember the elegant dance behind it. Data goes forward, error comes out. That error signal travels backwards, telling every single connection